All right, I'm going to go very fast. You know who I am. You know I work at Bloomberg. You know I've written a few books, and we're not going to talk about those today because I have to get through this really quickly. I did once upon a time give a talk about the birthday problem at ACCU, and it was very interesting. We talked about how we could write something like this, and gee, at some point it just stopped working, and we didn't know why. Well, it turns out that a double can't really express things very close to 1, but it sure can express things very close to 0. And if we just take a quick look here, we'll see why that might be. That's close to 1, but if we look at this, we'll see, we can express things very close to 0. So it turns out that if we just rewrite the problem and we call it unique birthday, then it just works perfectly and we're very happy, problem solved. Now what I need to do is I need to talk about today's talk, which is how much of the world's water is dinosaur pee? And there's some related questions. Meet my stepdaughter, Ava. We got into this big discussion about all the different things that might be involved, like how long they were, how many they were, how much time went by, and so on and so forth. And we got to the thing like, what's the probability that every molecule of water in the planet is dinosaur pee? So some questions. Assume that we have uniform access to water. How much of the Earth's water is dinosaur pee? And there's going to be 5 answers. It's multiple choice. 0, almost 0, some, almost 1, and 1. That's the answer for all of the questions. The second question is, assuming, or what is the probability that all molecules are dinosaur pee? Again, the same 5 answers are available. And the third question is, suppose the expected amount of untainted water through some calculation turned out to be on the order of the mass of one water molecule. What would be the probability that all of them are tainted? And so same question. And fourth, suppose I had a 8-ounce glass of water, what's the probability that it's all pure? Those are the 4 questions. So just to recap, here they are. Record your answers. What fraction is water is pee? What is the chance every molecule is pee? What if the answer to 2 is all but 1 molecule? And the fourth one is, what is the chance that the cup of water you're drinking is pure? So now we have to go answer these questions. I couldn't answer it right away because I was working on this book. So over some time, I accumulated some facts. It's an open question how much dinosaurs drank, but we took a couple of possibilities. So I did some of these, little back of the envelope calculations. And bottom line is, and I have to go quickly, bottom line is like this. So that's what I came up with. So with that, we did a little calculus, and it turns out that you can just plug it in, and there's the rate, and so we just plug it in, and we get, and the magic answer is, okay, so about 3.11% is untainted, which means that the answer that we were looking for the first is probably maybe D-ish. Almost all. But it turns out that maybe we should have done it by a different calculation. We should have done the daily rate versus the yearly rate. Turns out it makes no difference. And there are other models. We could try a discrete model, and we could do this, and the thing about continuous compounding and all that. It turns out that doesn't make a difference. But then there was somebody else who tried a different model, and they used birds, and they came up with 10 times the consumption that I did. So I said, all right, fine, let's plug that thing in, and that gave a rate that was 10 times as much. And this calculation, they tried to use a discrete model, and of course it blew up because that number is way too small. You can't represent that number. It's just broken. So we represented it the way we do it, and here's what we got. So the answers are, in their model, you can see it's anywhere from 3.11% to like nothing. Like there's 17 liters left. All right, So anyway, that's that. What's the chance that all of it is P? Well, this is a summation, and I'm just going to click through this because I don't have time to explain the difference between expected value, but if you're throwing coins, you can imagine that it's sort of symmetric here, but not all expected values are symmetric, and this is a case where that isn't symmetric. For example, this problem here when you're dealing with the number of leading bits, that's not that way. The expected value is there, but you have a probability density function. So we were able to calculate that. We used some other facts, and lo and behold, we just distributed, and that P turns out to be the probability that any given one molecule is what we're talking about. We did a little more math, and we get this number, and that's a number with a heck of a lot of zeros before you get a 1. That's a really small number. You can't represent that with a long double. So there are the answers to that. And final answer was almost B for that. Then the third one was just a little math, and it turns out surprisingly, whoops, I went a little fast, that both this and this are the same, but the answer is 1 over E, just in case you care. So that one's in the middle. And then the final one, well, we just plugged it into the same thing, and we got that. So how did you do? Here are the 4 questions, and there's none of those on the end. right? Because there's nothing 0 or 1 in this world, but those are the 4 answers. And so the takeaways here is dinosaurs created a lot of pee, molecules are very small, and it's interesting who won. The molecules won. Even if there's no expected water left, the probability that all the remaining pee is so vastly small that you can't even think about such a number. And just like the birthday problem, if you try to subtract a very small number from 1, it's not going to work out. And that's me eating steak right before I gave the talk at ACCU. And it's a dino steak. It said so on the menu. Thank you very much.